It's a great honor to speak in this conference in celebration of Esnault. I was fortunate enough to be a student in her group in Berlin, and this is something that has had a very great positive impact on me. So the topic of my talk will be something about vanishing theorems in positive characteristic. And vanishing theorems is a subject that Hélène and Esnault, together with Eckart Viehweg, made important contributions to several decades ago. And their joint book, Lectures on Vanishing Theorems, is still today the go-to reference to many of these things. And my talk today will be sort of close in style to those lecture notes. So the protagonist of my talk is the following theorem, which is due independently to Kawamata and to Viehweg, both in 1982. So this is a theorem over the complex numbers. So X is a projective smooth variety, and delta is an effective divisor with normal crossing support. And the coefficients of delta are less than 1. And if we have a divisor that satisfies that L minus kx minus delta is big enough, then all higher cohomology of L vanish. Okay. And so there is, of course, a version of this where if we have no divisor and L minus kx is ample, then this is due to Kodaira. And we usually call this version, which has no divisor here, Kodaira vanishing. And this version where we allow for this extra divisor, Kawamata Viehweg vanishing. So,
what does it mean that the coefficients are distant?
So this is a divisor, so it is a sum of some reduced divisors with coefficients, and these coefficients should be between 0 and 1.
Rational numbers?
Yes, so you can irrational numbers. Yeah. Okay. So yes. Okay, so this theorem, of course, I've had a lot of applications in algebraic geometry, but in birational geometry, this generalization of the Kodaira vanishing theorem of Kawamata and Viehweg is really the one that is important in applications. So this extra boundary delta, this extra freedom that it allows, is really what we need usually in birational geometry. So I'm just going to say a couple of words about this. Okay. So in the context of the minimal model program, you start with some variety and then you do some birational transforms until you end up with another variety that should be simpler, but you will always have introduced singularities, okay? And so these singularities that you introduce in this process, they are described as pairs. So this is a normal variety again, and this is a divisor. Effective. And we can characterize these singularities that appear in the context of the minimal model program in the following way. So if mu is a log resolution of this variety together with this divisor, So we have a y, and then we have a birational transform of this divisor plus the exceptional. Okay, so this is a log resolution, means that this one is smooth, and this is a normal crossing divisor. And then, so we additionally also here assume that kx plus delta is Eckart. Then if we pull back this pair here, then we're going to have the canonical on y, the birational transform, and then we're going to have something exceptional. And these singularities that appear in the context of the minimum order program, they are characterized by this whole part having coefficients less than 1. Okay. So, so this is just the birational transform of delta.
It's just a rational. It's just a
yeah. So if you want, this is isomorphism on an open, and then you take the preimage and the closure. That's the yeah. Okay. So this is the notation. Sorry.
proper transform.
Yeah. Exactly. Proper transform. So these coefficients less than 1. So then x delta is what is called Kawamata log terminal, which is precisely this class of singularities. Okay. So what I wanted to say with this, I'm not going to talk much about birational geometry, but what I wanted to say is that you see that these kind of pairs, they have they pull back precisely to the kind of pairs where that this vanishing theorem holds for. Okay. So a consequence of this is that the relative version of this theorem of Kawamata and Viehweg. So I will call this Kawamata and Viehweg vanishing now, and shorten notation KVV. And this slash is to say relative over x. So the relative version of this actually implies, just for this reason, that KLT singularities are rational singularities. Okay. So this is one of the reasons that this theorem is so important in birational geometry. And another consequence of this is that we see that actually this theorem of Kawamata and Viehweg, it also applies to singular varieties. It also applies to these kind of varieties. Just because we have a relative version like this. Okay. So KVV prime, I'm gonna call, so says that if x comma delta is KLT and L minus KX minus delta is big enough, then again all higher cohomology vanish. Okay. So this is the version of Kawamata Viehweg that we will be discussing. We will allow for singularities. Okay. And of course, there is also a singular version then of Kodaira vanishing. So then we allow for x to have KLT singularities, and we ask for L plus KX to vanish. Okay. Okay.
Is L bar T is what N? So before N, can't we? Is
KLT?
Is what K?
KLT. So this is Kawamata log terminal. So this is precisely this class here. Yeah. So the definition that I gave you of KLT is that if you look at the log resolution, all the coefficients here have to be less than 1. Okay. So now, of course, we will discuss what happens in positive characteristic. So in positive characteristic, very famously, we do not have these vanishing theorems. Already Kodaira vanishing is not true already for smooth surfaces. So This is very famous, and the first characteristic P, Kodaira vanishing fails, and the first examples of this were due to Renault. Okay. So the examples of Renault were surfaces of general type, and people sort of expect in the beginning that, so for example, if you look at smooth del Pezzo surfaces, you sort of directly see that Kodaira vanishing holds on them. And so you expected that probably there are maybe some bigger class where you actually have these vanishing theorems. So maybe this, and so maybe, for example, you expected that for smooth rational surfaces, maybe you have these vanishing theorems. So it turns out that that is not the case, actually. So I want to mention the following examples. Okay. So in 2018, so much later, Kashini and Tanaka show that over every field K of characteristic P, there are smooth rational surfaces that contradicts this more general version of Kodaira vanishing, so this version of Kawamata, Viehweg, KVV. Okay, and their construction also shows that in characteristic 2, also Kodaira vanishing fails on KLT del Pezzo. So these things are slightly complicated. So you see there is a difference if you look at in the smooth case between having KVV and having Kodaira vanishing, and then there is also a difference between having Kodaira vanishing for a smooth del Pezzo, which of course hold, and then we see that allowing these singularities that are very natural in this context, you don't even have Kodaira vanishing anymore. So this is okay. So, however,
is it something like a Nati Shire cover of P2? So what are these?
So for this one, you take P2 over FQ. So Q is P2D, and then you take all the FQ rational points, and then you take all the FQ lines, so all lines defined over FQ, and then you blow up all these FQ points. And then you look at the birational transform of all these FQ lines, which are now actually minus Q. They have self-intersection minus Q, because there was a lot of points on all of these lines. It's a configuration of lines that you cannot have in over complex numbers. And then you contract all these minus Q curves. And that is... So the smooth one that contradicts Kawamata Viehweg is the one which has the minus Q points. And that is the divisor that you're going to use here to have a contradiction. And then if you contract them, you get a singular thing that doesn't have Kodaira vanishing. Okay. So there, interestingly, there is the same authors shortly after showed the following positive result. I think this is also to 2018. So again, this is Kashini and Tanaka, but now also with Wittacek. And they show that there is an integer, so I will call it P02, but it's just an integer, such that for every perfect field K of characteristic P greater than P02, and every log del Pezzo over such a K, such as for every perfect field K, so for every log del Pezzo over K, Kawamata Viehweg vanishing holds. Okay. And their methods were such that this P02 was completely implicit, and there was no bound on this.
Is a log del Pezzo?
Yes. So no. So I'm going to define this. Yes. Okay. So log del Pezzo. So this just means there is a delta such that x comma delta has these KLT singularities, and minus kx minus delta is ample. Okay. So this is definition of log del Pezzo. Okay. So this again allows these singularities, this class of singularities. Okay. So this is quite interesting, and so one could, maybe I put it here, ask the following question now. So is there some integer depending on the dimension such that log Fanos satisfy this Kawamata Viehweg vanishing for perfect fields in characteristic P greater than P0n. So the only thing we know about this question in higher dimensions is that P0n would need to be greater or equal to n plus 1 over 2. So it has to be increasing with the dimension, because there are some examples of Totaro of Fanos that contradict this vanishing. So this is for n from dimension 6. He has constructed examples where this vanishing theorem doesn't hold in the characteristic equal to this.
Excuse me. Log del Pezzo, delta is effective.
Yes, delta is always effective here. Yes.
I'm sorry.
Yes.
But it's not necessarily a normal crossing divisor.
No, exactly. So yeah, so it's really just the way to think about this is really that there is a log resolution where the coefficients still are less than 1, and yeah.
Okay.
Yes. Okay. Okay, so this is the, let me just check the, yes.
So in higher dimension, you assume there exists a log resolution and also a positive characteristic?
To ask this question, you don't need to assume that. So there is a completely resolution-free definition of KLT singularities, which doesn't depend on resolution, which I agree with this resolution if resolution exists. But I'm going to talk about dimension 2 and 3, and so I thought that I would just let KLT singularities be defined like this. Yeah. Okay. But there is nothing dependent on resolution in this. Yeah. Okay. So yeah, so I wanted to say why people are interested in this question, right? Because maybe it seems very particular, because okay, you don't have vanishing theorems in general, so why do you care if you have this in some kind of class? So the interest in this question comes from the relationship between having vanishing theorems on Fanos and the properties of these singularities that appear in the minimal model kernel, so KLT singularities. And so, for example, you have the following. So in dimension 3, there is a theorem of Hélène and Viehweg that shows that KLT singularities, dimension free, KLT singularities are rational in characteristic greater than this, whatever is the characteristic such that you have these vanishing theorems for Fanos. Okay. So there is this relationship between properties of KLT singularities and having vanishing theorems for Fano, and this is why one is interested in this question from the perspective of birational geometry. Okay. Yes. So my talk today, what we are going to go through is a proof that this P02 is equal to 5. Okay, so this is what we're going to do today. So today I'm going to show that P02 is equal to 5. And this is not going to involve much birational geometry. Okay, I think. Any questions? Yeah?
What is n?
Dimension. Sorry. Fanos such that n-dimensional okay. Sorry. Okay. Okay, so today we are going to talk about so I'm going to say a little bit about higher dimensions in the end, but today we are basically going to talk about the proof that this P0 in dimension 2 is actually equal to 5. So we're also going to see that this is completely strict. So we have a failure of this vanishing theorem up to characteristic 5, and we don't have after characteristic 5.
Yes? Do you call dimension 3 when there's a bound for 2?
That's a theorem.
That is it. Okay, thank you.
No, so in dimension 3, KLT singularities in dimension 3 are related to vanishing theorems in dimension 2 on Fanos. And so in general, one expects that properties of KLT singularities in dimension n+1 is related to the existence of vanishing theorems in dimension 1. Yeah, so yes, but I think. Okay, so now I'm gonna discuss how one can show this, and so one way to assure that we have some vanishing theorems in positive characteristic comes from this seminal paper of Hélène and Emelie, and this is actually the approach we are gonna take here. Okay, yeah, let me write here. Okay. Okay. So if x over k is smooth and the characteristic of k is p, which is greater than the dimension of x, then if x lifts to w to k, then the Kodaira vanishing theorem holds on x. And there is also a boundary version of this, which allows you to discuss the Kawamata Viehweg vanishing theorem. So the boundary version is that if x comma delta is, so we call this log smooth. So I mean by that this is a smooth and the support of delta is normal crossing. And then if L minus kx minus delta is ample and x together with this normal crossing divisor lifts to w to k, so this in the sense as discussed in the lecture notes of Esnault and Viehweg, then so again, of course, we should have the same assumptions. So the characteristic is P is still greater than dimension.
Excuse me, but in the other statements, I think P equal to dimension of x is okay.
Ah, okay. Sorry. Sorry, my dimension is 2, so I somehow. Sorry. Okay, so I guess that will probably follow over here as well. Sorry, I'm sorry. Okay. And then if L minus K minus delta is ample, then X comma delta and X comma delta leads to W to K, then we have this KVV statement. Okay. So, from the perspective that we are going to take here today, the sort of difference that we have seen between Kodaira and Kawamata Viehweg being true for different smooth surfaces is the difference between a surface allowing a lift and a surface allowing a lift together with a simple normal crossing divisor. And so this is how we can understand, for example, examples of sort of smooth surfaces that are lifting but still contradicting KVV, because we cannot lift the divisor. And this also actually, so I mentioned that smooth del Pezzos, of course, you have Kodaira vanishing, but then we saw already an example in characteristic 2 where these KLT del Pezzos do not have Kodaira vanishing. And again, this kind of difference between singular del Pezzos and smooth del Pezzos having vanishing also comes from this, the non-possibility of lifting some divisor. Okay, so I wanted to go through an example of this. So we are going to look at an example in characteristic 5 of a del Pezzo, which fails, where Kodaira vanishing fails. So we KLT singularities. Okay. Because I think this sort of illustrates very well where this kind of behavior comes from.
Excuse me?
Yes?
The way the P0 of 2 is defined, you need a counterexample in characteristic P0 of 2. So in characteristic 5 in your case. But does it also fail in characteristic 2 and 3?
So far I haven't said anything. Okay, yeah, okay, sorry. Now I understand your question. Okay, yes, okay, yes. So this example I'm going to go through is the example in characteristic 5. We also have examples in characteristic 3 and 2. And so the 2 is the one I mentioned there by Kashini and Tanaka. And then in characteristic 3 there is an example of Fabio Bernasconi.
Okay, so although the P0 of 2 as it's defined is only the sort of the maximum where it's failing, you can have failure all the way to it.
Yes, exactly, yeah. So it fails in every characteristic that is less than 5, and it holds in all of them that are greater. Yes. Thank you for the question. Okay, so we are going to look at the rational elliptic surface that comes from William Lang's classification of rational elliptic surfaces in positive characteristic in 91. And he also actually writes there that this particular surface was found by someone of Schuen. Okay. So this is a elliptic surface. So the notation is like this, and it has 3 singular fibers. So two of them are these cycles of rational curves, and then third singular fiber is a nodal fiber. And this surface has integer coefficients, and then interestingly, if you reduce this modulo p, then for p greater than 5, you still have a surface of exactly the same type. But when p is equal to 5, you have something else. So in p equal to 5, this node becomes a cusp. And so you have the surface that looks like this. Okay. So now what you can do is the following. So now if you look at this surface in characteristic 5, you can just resolve this cusp. So I want to have another color here. Okay. Yeah, okay. Okay, so you resolve this, and so you have a birational transform of this curve together with the birational transform of two previous exceptional divisor, and then the last exceptional divisor here.
Sorry, what's this dotted line?
So this is just this is 5 rational curves, and I want to draw the one that is, because it's a cycle. I'm drawing it like this to give a three-dimensional feeling to it. Okay, but now, anyways, we are gonna actually directly contract the section here, so we can stop having this. Okay, so we have this, and now something that looks like this. Okay.
No, I meant I don't quite get the picture. I mean, the resolution is supposed to be connected or something, right? When you resolve the cusp.
Yes, so when we resolve the cusp, so in the first step, we have this, and then we have this, and then we have this.
Okay.
Yeah.
Those are all going through the bicycle.
So this is just, yeah, okay. So maybe my artistic talent can be questioned. Don't know. Okay, so maybe, okay, so here we resolve cusp, and we also contract the section. Okay, so, okay. So then, actually, because we contract the section, we have it's like that. We first resolve and then contract the section. So yeah, okay. Now this is going to be the minimal resolution of something that has very bad behavior. Okay.
But when you contract the section, don't all the fibers go through the same point then?
Yeah. So okay.
I'm just making clear. They're all supposed to go through the same point.
Yeah, so I contract this a section, so I assume that this section was going through here, and then here, and then I draw this line as now, okay, so going through here.
Gotcha. Okay. Thank you.
But I will maybe draw a new picture where it's more clear what I...
The section is a -1 curve?
Yes.
The one.
Yeah, the one yeah.
Can I just say, you do have some better colors on the board?
Ah, okay, perfect. So yeah, so that I will use now then. Thank you so much. That's perfect. Okay, so we have a surface. So we have these four curves, and then we have this three here now. Okay, so these are -2 curves. This is -2, -3, and -5. Yes. Okay. So now this is still a smooth surface, and we are going to contract all these blue curves. Okay. So contract blue curves. And so we are going to get these 3 singular points and then to A4 singularities. So we have a surface now that is going to be called X that has 5 singular points. So this X is minus Kx is ample, and X is going to have KLT singularities. And now actually already now you can see that something strange was happening, because in this situation actually over the complex numbers we cannot have 5 singular points. So there is something called the Bogomolov bound that tells you that you have to have less than 5 singular points. Okay, and indeed something strange is happening. This surface X, X is, as I said, a KLT del Pezzo that contradicts Kodaira vanishing. And so how do we want to understand this? So of course we started with this surface living in character 0, and then we did some blow-ups, and so of course here we also have a smooth surface that lifts, right? But these exceptional divisors, they do not lift, okay? So this log resolution of this surface does not lift, because we were producing this situation by performing blow-ups that could not have been performed in this way in character 0. Because so for as one can learn in the lecture notes of Esnault and Viehweg, if you have a simple normal crossing divisor that lifts, then you can always choose some local coordinates that describes the simple normal crossing divisor as just vanishing of product of these coordinates. And so the lift has to also be described in the lift of those coordinates by the exact same equation. So incidence relations has to be preserved. And this is not the case here, because if you blow up the node, you do not get, you can never get these configurations of curves. Okay, so this is indeed what is happening. So what we are going to use here now is the following. Yes, and so I should also mention this. I mean, this was a question, but I wanted to mention here also. So, a log del Pezzo surfaces that contradicts this vanishing has been now constructed in character 2, so this example I mentioned in the beginning, then character 3, this is due to Bernasconi, and then character 5, this is this example here. Okay, so
so when you talk about lifting delta, do you want each component to lift individually, or are you just okay with lifting, like, can the lift smooth?
So I talk about this all the time for the log smooth, in the log smooth situation, and I mean precisely the sort of definition in Esnault Viehweg. So you can really think about this as you have just locally vanishing of some coordinates, and the lift that you're going to have is going to be described exactly by the same equation. And this, so the definition is that each of the components should have flat lift. Yeah. So yeah, we really, yeah. Okay.
And I apologize. This example does not work in characteristic 2.
No, so this example is really characteristic 5, because if we reduced also, I didn't mention it, but also in the lower characteristic, you will have also the node there. You will not have a cusp.
You have also?
The nodal fiber will stay nodal.
Yeah, I understand, yeah.
So it's only in case 5 that you get this cusp, because the Hessian matrix has a 5 in the determinant.
Can't you find an example which does it for all the bad characteristics?
But
I think the examples are different in each of the characteristics. Yeah.
Is it always like in 2 and 3 of this type, like some elliptic surface, maybe a different type, and then you contract the?
So I mean the characteristic 2 example, this was a configuration of this line, so this was not, and the characteristic 3 is also not from an elliptic surface. No. Yeah, but somehow what I would say is that it's all the time about some divisor that, so it's all the time about a configuration that does not look the same somehow. So in this configuration of lines, this is not lines, you cannot have lines in characteristic 0 that intersect in that way, and sort of similarly this is what's happening here. So yeah, at least this is the perspective I'm taking here. Okay. So for surfaces, we have the following. If if x comma delta is KLT and L minus KX minus delta is ample, and x comma delta has a log resolution, that lifts to W2K, then all higher cohomology of L vanish. Okay, so this we just had on this board here in the case when x comma delta itself was log smooth, and so for surfaces here we have this also for KLT pairs. So this actually uses a relative vanishing theorem that is true for surfaces. But what I wanted to say with this statement is that the intuition here, this is completely true. For surfaces, because we directly see, because there is not Kodaira vanishing on x, we directly have that we cannot have that the log resolution of x lifts. Okay, so for surfaces, this is really what we want to show here. Okay, so I can now state the main theorem. Okay, so the theorem is the following. So if x is log del Pezzo, so there is some boundary giving it the log del Pezzo structure over K, so now K is going to be algebraically closed of characteristic greater than 5. Then if we have a boundary such that this is KLT and a set divisor with L minus kx plus delta Fn big, then the statement is that there is another boundary such that we still have that L minus kx plus n. Actually, this is ample, but then the important thing is that x comma n has a log resolution that lifts. So the theorem actually is that it lifts all the way up to character 0, so it lifts to wk, but also in particular to w2k. Okay, so not only do log del Pezzo surfaces have log resolutions that lift, but we can also lift boundaries on them in the following sense, in the sense that is needed to show this vanishing theorem. Okay, so what is a consequence of this? So of course, a consequence of this is now that yeah, with the log resolution, I always mean smooth together with normal crossing divisor. Okay. And I only talk about liftability of such pairs. Yeah. Okay, so this is saying that so the log resolution is going to be smooth, and the birational transform of this divisor is now going to be normal crossing, and the exceptional divisor is going to be normal crossing. Okay. And that whole pair lifts. And this, of course, then implies that Kawamata Viehweg vanishing holds on all of these surfaces. Okay. So, yeah, let me discuss the proof here. Okay, so the reason I like to discuss this proof is because I feel like the main idea from this proof really comes from the lecture notes of Hélène and Eckart Viehweg. So we will need to use the following sort of lemma. Okay, so as I already mentioned, when we are lifting a log smooth pairs, we always know that the lift of the normal crossing divisor is going to be a normal crossing divisor given by precisely the same incidence relations. And for this reason, if we have a log smooth pair and we blow up a point, then of course in general, if you blow up a point, you can lift that point in many, many different ways. But when we have a normal crossing divisor, we can just describe that point locally as in the local coordinates that we're choosing. And so we know precisely which point on the blow-up we should blow up to preserve exactly these incidence relations. So the lemma that we are going to use is that if x comma delta is, so maybe support of delta is log smooth, and y to x is blow up at the point x and x, so sorry, it's log smooth surface, and y to x is the blow up at the point x and x, then if this pair lifts to w to k, then also, of course, the blow-up lifts, but also the birational transform or the proper transform of this divisor lift together with the exceptional divisor. And so here, there is not this problem that we are doing blow-ups that are not allowed, because we have this simple normal crossing divisor that tells us precisely what is the point that we're going to blow up on the lift. And if we do that, so in local coordinates, it's completely evident that if we look at that blow-up, when we reduce it to characters p, we get precisely the blow-up of our original pair. So it's really important here that we are talking about these log-smooth pairs, okay? So this dilemma is, completely evident, but we are actually going to mostly use this over and over again. Okay, why
is it completely evident? It's not evident.
So I guess it's completely evident if you know that. So x is smooth. So let say x1, x2 be étale coordinates, and let support of delta be the vanishing of xi. So how can I say so? Xi, xj, and this I and j are either 1 or 2 or empty set, so to say. Okay, so this is how this divisor look like. Then if you wanna, then the lift has étale coordinates x1, x2, where the lift of this one, this thing here has is described by precisely the same. Okay, so now you're gonna blow up. So the blow up of the lift, so x tilde at the point x1, x2, this is clearly going to be something that, yeah, okay.
Okay. It's local, and you mean that there's a global lifting?
Yeah, I mean, I assume that, right? So I'm saying if this one lifts, yeah, so if this one lifts, yes, it's just about being able to choose the right point to blow up, because, yeah. So definitely we already know that this one lifts, so the blow up at any point, yeah, that we want it to be the lift of this blow up, yeah. Okay. Okay. Okay, so okay, so sorry? Okay, sorry, yes. Okay, so the okay, so I think okay, let me. Okay, so x. So we are in this situation of this statement here. So x is of is log del Pezzo. This implies that we can run an MMP for every divisor on X, and this is because this is what is called a Mori dream space. You can run MMPs for any divisor. So MMP just means that we are contracting delta negative curves until eventually this delta has become NEF. Okay, so this is what is meant with the delta MMP, and because we are on the log of the Pezzo, we can do it for any delta. So delta is going to be the delta in our KVV assumption. Okay, now our delta, we can write it as the pullback of this delta y plus some n, and this n now is going to be pi exceptional. Okay, so I'm just saying that delta is whatever survived plus something that was contracted. That's it. Okay.
But you mean the proper transform of the delta y or the whole?
No, this is the difference between the pullback of delta y and delta.
Oh, okay.
Yeah. Okay.
Essentially means strict transform. I'm not sure.
And so this now, if we look at
can you say that? So what is pi over star delta? That's a strict transform. Or?
No, so this is actually the pullback here.
That's a total pullback.
Yes.
Okay.
Yes.
So the n is a residual part.
Yes. Yes. Okay.
You're saying n is effective.
Yes, n is effective. Okay. So if I look at this now, L minus kx plus n, then this is just L minus kx minus delta about so if I so n is just delta minus the pullback here, so I have delta minus the pullback, so I have to add the pullback as well. And so this here now is ample, and this one here is NEF. So this whole thing is ample. Okay. So that is not. So I should also mention, sorry. So we can actually directly assume that L minus kx plus delta is ample, because when we have this kind of divisor, and the class of KLT singularities is open, so we can always change the divisor a little bit to get ampleness. Okay. So basically, this is going to be our n that I'm going to show now that lifts. Okay. So that is the point I want to make. Okay. So we have this situation, and then sort of the first part here that I did not have time to discuss is that we actually show that, so this y here is still going to be log del Pezzo. So the first part is to show that the log del Pezzos have log resolution that lifts if the characteristic is greater than 5. Okay, so this we show more generally for a more general class of surfaces, and that more general class of surfaces they satisfy then Kodaira vanishing, but they do not necessarily satisfy Kawamata Viehweg vanishing. So what I'm gonna sort of go through with you is how to get this boundary in this statement for log del Pezzo surfaces. Okay, so the first part of the proof is to show that all of these log del Pezzos, they actually have log resolutions that lift. Okay, so the second part now is that you have this induced rational map, and you can perform a sequence of blowups to resolve the indeterminacy locus of this map. Okay. And then you simply use the lemma to say that this whole thing is going to lift. Okay. And now the last step is that we want to show that x with this boundary n has a log resolution that lifts, right? So we want, so let's call this map, so this is map is mu and this is mu prime. So we want that v prime with the exceptional of mu prime and the proper transform of n, that this is a log smooth pairs that lifts. Okay, but now we just have to look, what do we know? We already know, just by applying this lemma that I was talking about, that this divisor here lifts. But what is contained in the support here? So this is everything contracted by mu, rational transform, and then everything that is contracted by pi prime. And so it's everything that is contracted by v prime to y. And now we just look, so this n is contracted by pi, right? This was our assumption. N was everything that was contracted. And of course, the exceptional of u prime was contracted. And so this whole thing, the support of this is contained in here. So it is simple normal crossing, and it lifts. Okay. So this was what I wanted to say. And so really from this perspective, the special thing about log the Pezzos is actually that they are a class that behave very well with respect to the minimal model program, because this is what allows you to actually lift these extra divisors. Okay. So thank you so much for the attention.
Thank you very much. Are there any questions or comments? Yes?
So can you say a little bit about the first part? Because that's the only place where the characteristic 5 comes in.
Yes, so that's a very good point. So for the first part, so this is more general. So for the first part, this holds. So the first part actually say that if kx is not what is called pseudo-effective, and then there is a logless solution that lifts. Okay, so what is meant with this pseudo-effect? It just means that a kx MMP is going to end with y, and so either y is going to be del Pezzo of Pickard rank 1, or it's going to be a more fiber space, so this is minus ky is ample over c. Okay, so this is what is meant to be correct. So anyone that has an MMP that ends like this has a log resolution that lifts. And how do you show this? So for the little Pezzo of Pickard rank 1, this I would say is the what has not been available previously, and this is from classification. So this is a classification made by Justin Lacini that shows that the Pezzo surfaces in the characteristic gradient of 5, it classifies this. They just are constructed in the same way as in characteristic 0. And then for the second part, so here comes, so I should, because you were asking about the characteristic. So the characteristic comes really from just this the Pezzos of Pickard rank 1, and for this one, if MMP ends with a more fiber space, then you have log resolution that lifts in all characteristic. Okay, there is no characteristic there.
So over an algebraically closed field of Pezzo, rho equals 1 is just P2, isn't it? Or is there
no, so we are talking about singular things here all the time. Yeah, so that is a huge difference. Right?
Okay, so you classify all those.
Yes.
Write them all down.
Is that related to the Klein singularities? They behave the same way in characteristic 0 and P, assuming P is more than 5, but in characteristic 2, 3, 5, they do not. You have the 13 covers. Is that related to that?
I do not know what Klein singularities is.
Klein is SL2 quotients.
Yeah, so I am not sure if it's related.
Isolated normal SL2 quotients.
Yeah, I'm not sure. I'm not sure if. Yeah, I'm not. I don't know. Sorry. It's interesting.
Another way is AN, DN, and EN. Another terminology is AN, DN, and AN, DN, and EN. I'm sorry. That's precisely those letters in English which are pronounced completely differently in all different languages. I'm sorry.
Any more questions? So you said it quickly, but what can you assume ample L minus KF minus delta?
Yes.
So what is the modification you do?
Yeah, so big enough. Another characterization of being big enough is that so D, say big enough. So for all epsilon, there is some ample AE and some effective divisor, such that D is AE plus epsilon E, and so these KLT singularities, they are also open. So you can always, if you just take a little bit of epsilon, you can add some little effective and still be KLT. And so basically, just by changing your boundary a little bit, you can assume that you're ample. So this is very. So this is why somehow in Kodaira vanishing, right, you cannot say there's a big difference between Kodaira vanishing for big enough and for ample, because you have no boundary. But in Kawamata vanishing, you have this boundary, and so there is not really difference. Yeah.
Okay. One question.
So I was wondering about your conjecture about the existence of P0 of n in general.
So I am not as senior as the other speakers. I do not make conjectures. This is a question.
So I was wondering, like, do we expect, some kind of boundedness for log Fanos over Z that would mean that we should always be able to lift for P very large?
Yeah, so depending on epsilon in that case, right? But yeah, so the boundedness in dimension 3 is also open, and if you have boundedness in dimension 3 for epsilon KLT, so there is also an epsilon there, you have to fix the singularity class, then that would imply that there is some P0 depending on epsilon, such that epsilon KLTs. Yeah.
So let's thank the speaker again.
Thank you.